We now formalize what we discussed in the previous video. So we're going to start with some definitions. Remember that we were after or wanted to motivate the definition of cardinality, and coming up. I mean, the whole point of the previous video is to come up with a notion that will allow us to classify different types of infinities, and for that we use an equivalence relation, and for that, I mean, we need to introduce a few concepts. I mean, you've already seen most of these, but it doesn't hurt to be reminded of. Okay, so if a function f from a set A to a set B is said to be 1 to 1, so I said if a1 not equal to a2 implies, well, I mean, just to be extremely careful, both elements in A implies, because I mean f is defined as a function from A to B, implies that f of a1 then must be different from f of a2. And also the function f is onto if for all b and b there exists an A element of A such that f of A is equal to B. So we can always find an A in A that is mapped via f to B. So again, a function that is both 1 to 1 and onto is a bijective function, and is exactly what we need to establish a one-to-one correspondence between the elements of one set and elements of another, and therefore allows us to say that they have roughly the same number of elements. Okay, so and then formalizing again what we went over. Also, definition 1.5.2 in the book. The set A has the same, or it should be said to have the same cardinality as B if there exists f from A to B that is 1 to 1 and onto. And onto. In this case, we write this. So, as I said, this establishes an equivalence relation. So this case we write A, B. A is related to B. And so now, well, we can go over some examples to see that. Well, in fact, before going over this example, let me just point out again, this is really a generalization of the concept of cardinality for finite sets. As we said last time, when if there is such a function, a one-to-one function and onto function between two sets that are finite, then, I mean, one of the sets is finite, there's a one-to-one corresponding to the other set, it has to be finite, but let's just say there are two finite sets, and there's a function that goes from one to the other, there's one-to-one and onto, then you know that when you count the number of elements, you'll obtain the same number for both sets. And so so the existence of such a function guarantees that they have the same number of elements. And so the counting number of elements or finding a function that is one-to-one and onto from one set to the other are about the same thing. And that's why, I mean, this definition here does not contradict the usual definition that we have for finite sets, because they both imply the same thing. I mean, two sets will have the same number of elements. To finite set, they have the same number of elements if and only if there is a function with these properties, this one-to-one and onto. So this is really a generalization of that concept. Now, the example they have in the book here, 1.503, is good in the sense that even though a set can be strictly contained in another, when you're dealing with infinite sets, you can still have the same cardinality. So they denote. So let's find E to be the set of even numbers, say. Okay, so even numbers in N. It turns out that E has the same cardinality as N. So the conclusion here is that there, instead of N, the E has the same number of elements in quotes than N. So there's a one-to-one and onto function from N to E. Okay, and how do you know that this definition is symmetric? Well, if a function is one onto, that there's an inverse, which will satisfy the same property. So finding a function from one set to the other is the same. Okay, and how does this work? So it holds that these two sets have the same cardinality. And how do we know that? Well, the set E is the set 2, 4, 6, 8, etc. The set N is the set 1, 2, 3, 4, etc. So here we can actually give a formula, a closed formula, for this map from E to N and vice versa. But just to be clear, in general, we don't expect to have like this very clean formulas that close expressions to write down the bijection going from one set to the other. This is not really important. The only important thing is you have a way of assigning or counting. That's what the word countable, which we'll mention in a little while, comes from. So how do you go from, say, n to e? In fact, there's a one-to-one correspondence, but so what about the function that goes from n to e that to x assigns 2x? Then 1 will be assigned to 2, 2 to 4, 3 to 6, 4 to 8, etc. And you see here that no place will have two arrows pointing to the same element, so the function will be 1 to 1. And each of these even numbers will have a pre-image, namely half of that number, which will be mapped to that. So this is so with this very neat close expression, we can derive one-to-one and onto mapping, a bijection between the natural numbers and the natural even numbers. Okay, again, keep in mind that not all the time you will be able to find a close expression like this. So here the function f from n to e to n, we associate to n is a one-to-one and onto mapping. And this graphic representation is something that is more useful in the next kind of example that we'll see. So the one important thing is that also some remark. Remember that we're not just gonna go over everything here for this chapter because it's not that important. So the remark here is that it can be shown that Q, the set of rational numbers, has the same cardinality as the set of natural numbers. The rational numbers and the natural numbers have the same kind of infinity. Okay, and in fact, C, the odd numbers, Q, and all these things, have the same kind of infinity. They all exhibit the same kind of infinity. And in fact, this is the smallest kind of infinity that you encounter. Because if you have an infinite set, then it's always possible to extract a subset that has the same cardinality as n. Think of it this way: if you have an infinite set, and if you take away one element, then there must be infinitely many left. Otherwise, the set would be finite. We're only finitely many of them, say like n or m. Then, if you put back the first element, you would have n plus 1 at most, or n plus 1, depending on how you name the cardinality of the set. So, of the remaining elements. So, whenever you take one element, you must have infinitely many left inside the set. So, if you continue doing this, you take another one, then there must be infinitely many left inside the set. And you can take another one, and if you do this, you will be taking a copy of n inside any infinite set. So n, the cardinality of n, is the smallest type of infinity you can encounter. There's no maximum type of infinity. You can always find greater infinities. In fact, if you have a set an infinite set. I mean, it's true obviously for finite sets, but it is also true for infinite sets that the power set has a cardinality strictly greater than the set. So if you look at the power set of A, then there's no bijection from A to the parts of A. You always be short and you always be shy many numbers or many elements. Okay, so the set, so this actually motivates the notion, I mean, the introduction to the notion of countability. The set A is said to be countable if the cardinality of A is the same as the cardinality of N. An infinite set that is not countable is called uncountable. There's a pre-logic, right? Either you can count the elements or you cannot, and if it's infinite, that means that the set is uncountable. Okay, so far we've seen that there are many sets that actually are countable. And our first example of a set that is not countable is R. So again, I mean, remember that we know that Q is countable, the integers are countable, but to the first set that we can find that, I mean the most important example, first thing that we should pay attention to, since we just constructed the real numbers, as I said, that included natural numbers, we may ask ourselves whether it has the same number of elements as n or not. As Q, I mean, it's a natural question, but maybe since Q has the same number of elements, or it has the same cardinality as n, then this is a very valid question. Okay, so and this is turns out not to be the case. So the set of irrational numbers, so the set of real numbers that are not rational numbers, is much bigger than Q. So this is a result that we really need to pay attention to. Okay. The set. So this is the second part of a theorem. Theorem 1.5.6 in the book. The first part is just that the set Q is countable. I'll leave up to you to look at the let's just use the same notation as them. Q is countable, so the second part is that R is not countable. As I said, I'm not going to stop to show that the set Q is countable. It's a very intuitive construction, this bijection. It does not follow a simple formula, closed formula, but it breaks down. I mean, the construction given in the book, it just breaks down into disjoint set. I mean, Q is expressed as a disjoint union of sets, and so you start counting all the elements in the first set and the second set. So you enumerate all these subsets of Q, the first set, the second set, the third set, and you start counting all the elements in the first one, then the elements in the second one, the third one, and so you see you can exhaust all the rational numbers. You can count all of them. So that means the function is onto, and since all these sets are disjoint, and inside each one of these sets, your function is 1-to-1, then the whole function is going to be 1-to-1. So therefore, you're gonna be able to conclude that Q has the same cardinality as N. So really, what we're interested in now is the second part, which is the real numbers are not countable. Because it actually uses some analysis. So the first part is homework, or I mean, I'm not going to rate it, but so you can leave it as an exercise. Okay. Useful exercise for you. And the second part, we're going to see this actually comes from the nested interval property. Okay, so suppose we were able to, so we could count the elements in R. So we can enumerate them, right? So we can the elements in R that is R is equal to x1, x2, x3, etc. Then in particular, the set 0, 1, both set 0, 1 would be countable as well. That is 0, 1 will be equal to y1, y2, up to infinity. We know it has infinitely many elements because it at least contains the rational numbers, right, which are already countable, the rational numbers inside the interval 0, 1. But since we're just picking numbers from here, you can have at most a countable subset of them. I mean, yeah, it can contain a subset of them, and that's a subset of a countable set can be at most countable. This is an exercise for you, but so we know that then 0, 1 is countable. So what we do is we define I1 to be, so I0 is going to be the set 0, 1, and we're going to define I1 to be a close interval not containing x1 and close interval with I1 contained in I0, so in I0, in I0, and so forth. So we produce a sequence of nested close intervals, right? So what the only point here is that you're gonna be actually taking away all the numbers from this set described in this way, but that's not gonna be possible because we know that the intersection of these closed intervals must be non-empty by the nested interval property. Okay, and here, well, this is, the fact that you can take choose or construct a closed interval with this property, so that I1 is contained in I0, and it doesn't contain x1. I'll leave to you as an exercise, but it's kind of easy. Look here. So this is the interval 0, 1. If this is x1, you just pick some closed interval here that does not. You can use the density of the rational numbers or the irrational numbers here, and you can choose some small neighborhood x plus 1 plus delta. You don't have to do anything explicit here. And the set here does not contain, you just need to include the endpoints here and here. And you have a closed interval that does not contain x1. And you keep going. And so in the end, intersection of all of these I sub i's or I sub k's with k and n, it's going to be empty. Why? Yeah, we have that this intersection is empty because by construction, if you pick any element here, so any element in 0, 1, so all this intersection is actually contained in 0, 1, right? Is contained in 0, 1. It's a subset of 0, 1. One of the sets is, the first set is 0, 1 closed interval, and so you have at most all these elements described here in this set. But none of these elements actually belong to that, because if you pick any, y sub k does not belong to y sub k plus 1. So it cannot belong to the whole intersection. Okay, so if you pick any element inside 0, 1, it cannot belong to the intersection, because it does not belong to I sub k plus 1. And remember, an element in such an intersection must belong to each one of these intervals, each one of these sets. So then the point is, well, okay, well, what about that? I mean, what's the problem with that? Well, but the nested interval property guarantees that this intersection is non-empty. So contradiction. And what's the contradiction? The contradiction comes from the fact that we assume that the interval 0, 1, the closed interval 0, 1 was countable. And so this is the problem. Okay, so the problem here just stems from the fact that this we assume that the set the subset of the real numbers was countable. And well, in fact, this subset 0, 1 has the same cardinality as R. I mean, you can see that. I mean, you can take that as an exercise, but it's an easy one. I mean, you can always establish that the one-to-one correspondence between R and the open set 0, 1 by using, say, artan or the function that they give you in the book, the example they give in the book, very explicit construction, just using a rational expression. And yeah, but that's the whole point. I mean, the set of real numbers is much bigger than the rational numbers. And as I said, I mean, try to read the whole section of the book, but aside from this application here, there's not much more I'm gonna be asking of you to understand. And one thing though, there's one problem. I think is the last one. We're actually asked you to show what I mean. Asking about why isn't there any contradiction when you try to do the same thing with Q and arrive at the conclusion this is not. I mean, this is not possible. I mean, the set Q will not be countable. I want you to look at that example and tell me if you see this part what the problem is, trying to reason the same way as we've done here. Okay, it's a good exercise for you and it's a potential exam question.